I'm going to start out with one of the classic problems, and there's a lot of different variations of this problem, but this is where a lot of people start statics out with, and that is with three vectors that all come together with a point. So the very first unit, everything, this is called concurrent, when everything comes together at a point. And you're given information for one of the vectors, and with that information you have to solve for the tensions and the forces in the other vectors. And when you have just three vectors, this is where you can use things like the triangle rule. So I'm going to go show you the triangle rule. We'll compare it to the method where you split it into a components, which is what you did in Physics 1, and we'll see which method seems easier, and I will let you choose whichever method you want to solve the problems, but initially make sure you know how to do this both ways, because it will save you time in the long run to learn all of these different methods for vector addition. So here is how you add those vectors together. We have this nice vertical force in blue, and you add these head to tail, head to tail. So we have the end of one arrow going to the tail of the next vector. And realize there's a couple of different ways to add this together. I could have added them on the right-hand side or the left-hand side, and either way everything has the same magnitude, which is the same length. Everything has the same direction, so it really doesn't matter which way you add them together, just so long as everything is head to tail. So call it a triangle or a whole parallelogram. However you want to see it, you'll get the same results either way. The next step for this is to fill in the angles, and a lot of times this is going to be the hardest step in the problem. Just copy it down just how it was in the original shape. So here we have 40 degrees with respect to the vertical. Look for similar triangles, so the same angle 30 degrees over here is the same over here, and just start filling in labels until you see where everything goes. Once you have two angles, getting the third one is just a matter of making sure everything adds together to 180 degrees. Here's our other piece of information we're going to add in. So what we know here is we know the length and direction of one of the sides of these triangles, and we know all of the angles for this triangle. After you have everything that's given in the problem statement labeled on your triangle, the next step is to decide which trigonometric functions you're going to use to solve for the rest of the problem. And the most commonly used laws are going to be the law of sines and the law of cosines. If you know all of the angles and just one of the sides, that's going to be easiest to solve with the law of sines. If you know two sides and the angle between those two sides, that's going to be the law of cosines. So in our case, we know one side, all the angles. Let's use the law of sines. And remember, the law of sines, we're just going to look at the length of one of the sides of these triangles divided by that opposite angle. So T1 is 50 over sine 40, and that is equal to the ratio of T2 over sine 30, which is the same as the ratio of T3 over 110. And we have just a one-line equation, and we can very quickly solve for the tension in this cable here and T3. Notice we have newtons labeled on here, and as well as the magnitude, we should also be paying attention to what angles these are happening at. So 40 degrees plus 50 degrees, so this is going to be coming up at 50 degrees. And then T3, of course, is all in the y direction. There's going to be lots and lots of triangles involved in statics. And if you're using the same relationships over and over again, it really does become convenient to just set a few tables up in Excel to do all of the calculations for you. So here is an example of a table that is set up for just any generic triangle where you know one of the sides, and if you know two angles, you know all three angles. So you can set this table up to fill in one side and two angles and have Excel automatically calculate everything else about that triangle for you, so you don't have to go through these calculations by hand over and over again. So pull open that Excel file and try it out in Excel. There are multiple ways to add vectors together, and it might seem tedious and redundant to learn all of these different methods. But know if you get solid in these early simple problems on the different methods, it's really going to save you a lot of time in the long run. So this is a very simple problem with just one little node where everything is coming together. When we get up into truss structures and bridges, we're going to be doing these kind of calculations over and over and over again for every single little bolt in that structure. And so knowing the different methods and which method is faster is going to really help you get through those future problems faster. So a little bit more work early on is going to save you headaches later in class. Okay, so if you've taken physics, you have probably learned splitting everything into components. So you have your force, which is a tension or compressive force, and you take that force and you split it into the X component and the Y component, and you're going to do this for each piece of it. So here's the next vector, and then we split this into the Y component and the X component, and here's our third vector, that's all in the Y component. And then after we've taken all the vectors and splitting them into parts, equilibrium says all of the x's and all of the y's have to add together to 0. So the next step is we're going to look at everything in the x direction and add those to 0, and everything in the y direction and add those to 0. Now I want to show you how this maps out to the triangle that we've created. So here are our x components, and you'll notice how these x components are equal and opposite to one another. So the top and the bottom of our box here are equal and opposite, and that's what leads to our equilibrium condition. Similar for our y components. Okay, so everything in the y direction here that's going up, so we have the green arrow has a positive y component, the orange arrow has a positive y component, and everything coming up has to be equal to everything coming down. And so if you line all of the vectors up head to tail, if everything creates a closed loop here, that is what satisfies these equilibrium conditions for everything in the x direction canceling out and then everything in the y direction canceling out. So you can kind of see how the triangle method of solving this problem is actually equivalent to the components method of solving the problem. It's just a very more visual solution to see how everything adds together. Let's walk through that component method once again, starting from our free body diagram. So this time I'm not even going to add the vectors into a triangle. You start by drawing the forces right on top of the picture, where they come together, label all the angles, and you're going to split everything into their x and y components. And I really suggest that you draw everything on your picture. So don't try and do this just by equations. Draw it on the picture, otherwise it's going to be really easy to make sign errors. So in this case, we have a negative sign on the x component, and you can only figure out that negative sign by drawing this vector and looking to see which direction it's actually going. So here is the first vector in the x and y components. Here's our next component, and you see we have a positive x force this time, and both of these have positive y, and those y forces are holding up everything that the stop sign is pulling down. So this is the first step. Split everything into x, y components, and you're going to use SOHCAHTOA to do this. So sine is opposite over hypotenuse. So your hypotenuse times sine 40, that's going to be the length of this side. Cosine is adjacent over hypotenuse. So cosine is going to be this adjacent side to your angle, hypotenuse cosine 40. So just really remember those SOHCAHTOA relationships to split everything into x and y. Once you have everything mapped out, you're going to apply the equilibrium position. So pick out everything in the x direction, add those together, and then pick out everything in the y direction and add those together. And you'll notice I have everything color-coded here. If you have a highlighter, that can help you keep everything sorted. So here's everything in the x direction. We have positive from T2, and then we have negative from T1, and these two components are going to add together to 0. So we can solve for T2. Here's everything in the y direction. We have positive and positive from those cables on the top, so plus, plus. And then T3 down is usually considered negative. So now we can solve for T3. So you can see here's all of the steps for adding together vectors with components, and we get the same results here as we got with the triangle method. This method of solving the problem can also be easily done in Excel. Excel is really nice for organizing everything in the x direction, everything in the y direction. And again, this is a very simple problem. We're going to get into situations in the future that are much more complex, has lots and lots of steps. You're probably not going to solve it correctly the first time. And setting it up in Excel makes it a lot easier to find that sign error or that angle you typed in wrong. If you do it this way, you don't have to resolve the problem every single time you find a mistake. It's much easier to debug it. So here's one way to organize it. What we're going to do is we're going to create one row for each of these forces. So here's T1. So T1 is 50. It has an x component and a y component. And we're just going to fill in the magnitude of that force. And right here for our x component, we can put in sine of the angle. Excel uses radians, so if you have the degrees in here for your theta, you can split that into radians by just typing radians. Here's our y component. That's going to be the cosine theta. So we've split our force into x and y components just right here in our Excel spreadsheet. Initially, we can fill in angles, we can fill in what this force is, and also look to see what zeros you can fill in. T3 is entirely in the y direction, so we know the x component is 0. Even if we don't know the magnitude of it, we know this is 0. And this is going to give us our next piece of information. We know for equilibrium conditions to apply, everything in the x direction has to add to 0. Now we have two unknowns in the y component. We have two unknowns here for our forces. We don't know what T2 is. We don't know what T3 is. But if we look at this x column, we see there's only one unknown here. So the only way for our x forces to add to 0 is if this little cell right here is going to be equal and opposite. So if this is negative 25, this has to be positive 25. So this Excel table gives us a way to start filling in our unknowns. And you just look at rows and at columns and then what you can fill in. If you know Fx, you can figure out what this other component of the force is. Once you know one side, so we're talking about this orange triangle now. If we know the x component, and we know this angle, we can figure out the hypotenuse. Okay, that's going to be Fx divided by sine of that angle. Next, we can figure out the y component, and you can continue working your way through this table. See, now we have just one unknown in the y direction. We know all of these have to add to 0. So you can just add these together. The negative is going to be this one, and that's our last 10. What this becomes is like a game of Sudoku. You just keep filling in rows and columns until you have all of your forces split into their x and y components and all of your angles. I think it's a nice organized way, and I won't force you to use this. So the homework is set up as just a Word file, or there are some Excel files where you can start filling these tables in Excel if you want to. So it's up to you which method you want to use, but a lot of my students have very much preferred this Excel method to solving problems. Wrapping up this first standard problem, let's compare the amount of work that is required in solving this with the method of components, where you add everything in x and y components, with the triangle method. So remember, for the components method, you first have to split everything into x and y components, and then after you have everything split together, add everything in the x direction, add everything in the y direction. So it ends up being kind of a long and involved process. And again, this is what you've used in physics, and so everybody likes to use what they already know, and it's sometimes hard to pry everyone away from familiar ground. But compare how easy. We have one line and you're done. Okay, you don't have to split everything into x and y components. There's no algebra for 2 equations, 2 unknowns. It's just one line and you're done. And it's very, very visually appealing, I think, to be able to see how those vectors add together and what is contributing the greatest to this force and how these are kind of fighting against each other. So take a long look at these two methods, and hopefully I can convince you to learn this alternative method, because down the road this will save you a lot of time if you can learn to draw these triangles. The next step. In this class, we're not just going to solve the standard problem out of the book. I want everybody to think it through a little bit more deeply and modify the problem for maybe some more real-life applications. So in this example, what could change this around? Maybe there's wind blowing, and this is, a real-life thing that could happen. Maybe there's a bunch of birds that decide to sit on the cable. Maybe there's an ice storm that's going to add some weight to it. As an engineer, you're not going to just solve one scenario and one problem. It's very different than what you see in a typical textbook. You have to think through all of the worst case doomsday scenarios and design accordingly. It's never for the average loading condition or the average use. You're always worried about those outlier cases and those kind of bad situations that might happen to what you're designing. So thinking through all of the different scenarios of what could happen in a system, that's really what engineering is all about, and that's what I want you to start doing with your homework sets. So instead of just copying the standard answers out of the solution manual, you're going to be thinking through the problems on a little bit deeper level. I'm going to give you a couple different examples of different types of modifications that can be done here. The first modification, this would be something that's just good. Initially, I'll give you a 90%, but in future homework assignments, after you're used to this kind of method, I'm going to bump this down to a B. A good modification would be just take one of the numbers and change the numbers around. What if tension was 100 newtons instead of 50 newtons? What if these angles were equal to one another? What if you were given T2 instead of T1? So if you just take one little piece of it, that would be just a good modification. The next step up, most engineering problems, you're looking for minimizing forces or when is the maximum force going to happen. So asking a question like, what angles would create the smallest tension? And this is the goal. You don't want a structure that is stressed out. The same weight can be supported by lots of different geometries up here. So what geometry would be the best? What geometry would create the smallest tensions up here? That would be a good engineering question to ask. So that would be a better type of modification for this problem. And I'll solve these here in the next slides. The best modification would be not solving for just one situation or another situation, but to actually graph out trends. And I will show you how to do this in Excel in the future slides. So maybe we want to see how these tensions are changing as the angles are changing. And this is going to give you the most information for how to design this the best. And that's the goal, is efficiency for supporting this load. Here's the solution for the first modification. The first modification, what if we changed this original tension of 50 newtons to a tension of 100 newtons? And this is going to be looking at similar triangles if you use the triangle method. It's the same equation, you're just plugging in a different number to the same equation and watching this triangle grow and shrink as you change the sides of one of these. And think through the implications of this. So, are these proportional to one another? Are they all changing with one another? And this will make you think through how these triangles are related and how these triangles are changing as the loads change. And sure enough, they are proportional. You just, if it's 50 to 100, you're going to multiply each of these results by 2. So you end up with the same triangle, the same angles. You just have a triangle over here that becomes twice as large as the original triangle. The next modification, we're going to set these angles equal to one another and decide what angle is going to create the smallest tensions up here. And for this one too, the way to solve it is to think about how this triangle is going to change as we change these angles. Draw a couple of triangles, and as we make those angles smaller, you see this triangle getting squished. And it becomes quickly evident that the smallest tensions will be created when we get rid of the x component of the force. The x component does nothing to support this weight. The x component is wasted tension, it's wasted stress in the system. So when you have a specific load to support, you want to support that in the same direction that the load is in. If we have 50 newtons down, straight up would give you 25 and 25. And any angles that aren't vertical, again, the larger the x component gets, the more you are stressing out those cables that are holding up your light. So this is another advantage of the triangle method, is you can push and pull that triangle and really start to get a feeling for what the best design should be and where you have wasted effort in your design. Finally, let's look at the best type of modification where we're going to graph out the trends. We're going to graph out what these tensions look like as we change the angle. And we now know what the best solution is. The best solution is straight up and down, but the world is not ideal. These cables have to span across a street. It's not practical to have them going straight up and down. And so let's see how those tensions are changing as we have to stretch these cables across our street. And Excel is a great way to graph it out. So let's just set these up. And it's the same equations that we've used before all we're doing is, instead of putting a number in for these tensions, we're just going to leave this as a variable. And I'm going to rearrange this equation to get something where we have the tension in those cables, and I've simplified it by making these two angles equal to one another. So alpha and beta are here equal, the tensions are equal, and this tension ends up being just sine times T3. So we're going to enter the weight of our stoplight in here, and then here is our angles in here. So tension as a function of those two angles, and we'll set this up in Excel to graph it. If you want to create a nice table and you want to label everything with angles and symbols, insert, symbol, you can fish around and find things like angles. So here's your heading, and what we're going to be changing here is theta. I'm going to put theta in our x-axis or in the first column, and these are just typing numbers in. Choose an increment, so I chose 5 degrees. You can just type in the first 2 or 3 numbers, so 0, 5, 10, and if you highlight this and then double click on the corner over here, just pull it down, and Excel will take whatever pattern you start here and continue that pattern for as long as you want. And we're going to change this angle from 0, which is the cable's going straight up and down, all the way to 90 degrees. So that's stretching straight across. So 0 to 90 degrees. If you need to widen one of the columns or any of the rows, you can just click on these edges. Watch a few YouTubes on Excel if you're not used to using it. The second column, we're going to enter the equation instead of a number. So tension as a function of angle. So I'm just taking this equation here, start with an equal signs, the angle we're getting from our first column, and if you double click on this corner, you can double click on it or click and drag, it will update this angle so that the next cell will calculate from the next angle, and so forth and so on. So you don't have to enter this equation over and over and over again. You just type it in once, copy the equation down, and it will update these cells automatically for you. So the next step is to have 2 columns, 1 column for X, our angles, and now we have the tensions that would be created from this angle. Now the top and the bottom, you'll notice that I've changed this from 0 to 0.01, and 90 degrees, things get a little bit crazy at 90 degrees. So these endpoints, we'll have to play around with these so that we can get a graph that's doable. Once you have all the data you want to graph in the table, highlight the table, go to Insert, and there's quite a lot of different graphs you can create. We'll just use a scatter plot. If you don't want to poke through all of these different graph types, just hit Recommended Charts, and Excel will look to see what you have highlighted and guess at what kind of graph you need. And we're going to just grab this very first suggested graph, the scatter plot. And right now it doesn't look too good, again, because of this last point. So we're going to have to play around with this last point a little bit before we can see what trend is going on down here. So here is our graph with a little bit better range. So I've bumped it from 90 degrees to 86 degrees, and that lets us see the trend fairly well on here. If you click on the graph, you'll see a couple of different buttons pop up here. This little plus button, you can format background colors and all kinds of things about your graph. So that's how I was able to add in the label for the x-axis, the label for the y-axis, and just click on anything in here to change it. You can right click to get all the options, or double left click to modify text. And again, if you're unfamiliar with Excel, just watch 2-3 minute long video of how to graph objects in Excel, and there's lots of different YouTubes out there for formatting. Let's zoom in on this graph a little bit and think through what it is really trying to tell us. 0 degrees, what does 0 degrees look like? What is 90 degrees? Why is it going crazy up here at 90 degrees? This is what the cable configuration would look like at 0 degrees. So this is 50, 25, 25, and you can see sure enough we're starting right here at half of our load. And as we increase the angle, so we're opening up our tensions here at the top. So here would be the 60 degree scenario. Okay, so at 60 degrees our tensions have increased to 50. So we have 50 in our cables, and that 50 gives us our 25s on each side. The doomsday scenario, if we keep stretching this out, we can never actually get to a 90-degree angle. You always have to have something here in the y direction because our load is in the y direction. And you can try this out at home. If you have a tug-of-war with someone over a situation like this where you're holding up a weight, you can put this on trucks or whatever you want to try and stretch it apart. You will never get a nice straight cable across. And it really is a tug-of-war game. As you increase what's in the x direction and increase this, you'll always need that little chunk in the y direction to hold up your weight. Looking at this graph, if you were the engineer designing this cable system, what would your suggestions be? What is the point of no return here? So would you tell everybody, don't go past 60 degrees, don't go past 70 degrees, and really you'd be looking at what your cables are able to support, and there's no specific cutoff here. So it's anybody's opinion of what to call the point of no return here. But initially, things aren't changing too horribly, right? So it is kind of right around 60 or 70 degrees here that you're going to have to really worry about things. Here's a little trivia question. Why is the Golden Gate Bridge so tall? Is this just for artistic purposes because it's going to look pretty standing up there above the clouds, or is there some physical reason that people designed this thing to be so tall? We'll have a whole unit on cables a little bit later on, but if you want to just boil it down to the basic premise of it all, what it comes down to is the problem that we just solved. So you have the weight of the road, and you can find the center of mass of this thing, and it's supporting this giant weight, and it's supporting that weight with a couple of cables. Now, what if those cables are coming in at close to 90 degrees from the vertical? Okay, as we make these towers taller and taller, what is happening to the tension in the cables? Now, of course, there comes a point of diminishing returns. You can't build this thing all the way up to the ionosphere, and you're increasing the length of your cables the higher up you build it. But there's a reason that those towers are so tall. So that concludes our example of what solving a problem looks like and what modifying that problem and thinking through a few other scenarios and a little bit more deeply about the solution looks like. Once again, for your homework, out of each section, you will first solve just one of these problems. So don't make more work on yourself than you need. Just solve one of these problems, and then you're going to modify that problem for some more realistic scenarios and think through what those numbers really mean. So this is more than just looking your answer up in the back of the book and saying, oh yeah, I got it right. Think through what it means, how you could design that system more efficiently, how those numbers are going to be dynamically changing, how you could change the angles or the structure of something. And it becomes a game. It's an efficiency game. So you have limited resources. You only have so much cable, and that cable can only support so much weight. And you have to take those limited resources and do the most with the least amount that you can. So that's the name of the engineering game. And I want you to play that game with each of these different homework problems. There's some more examples that are solved in the D2L webpage, so go through those to see some more examples, and let me know if you want me to make some more PowerPoints like this over any of these subject areas.